Okay guys, in the latest video I made, I wasn't able to understand how Stripe was able to handle 20,000 requests per second, around 3 billion requests in a day in 2022 on Black Friday. This was one of the topic on the case study that I shared in the latest video that I'm going to highlight here somewhere. But I wasn't able to understand in that specific video. If you follow to the end, I wasn't able to find a specific diagram of how this API integration API, this Stripe integration API works. So I spent the whole day just digging here on the Stripe engineering blog post, try to find some ideas on how this guy built this very cool API, and I found a specific um, entry that I'm going to study with you today right now, because I think this is one of the most important entries that makes that specific availability or SLA levels happen. So if you don't know what a service level agreement is, I covered those ideas in the latest video. But in today's video, we're going to talk what I think. I still researching this, but what I think is one of the most important reasons they were able to afford such a service level agreement of availability or uptime in those days. So let's read through and start commenting this. How Stripe documents databases supported 99.999% uptime with zero downtime data migrations. In 2023, Stripe processed 1 trillion in total payment volumes, all while maintaining an uptime of 999.999, which is 5 nines. This is seconds. This is seconds in a day, just seconds down in a day. Exactly, we can go here, and if you can see here, 4 nines, it gives you a downtime per day of only 8.6 seconds. Okay, so you can imagine how good these availability metrics are. We obsess over reliability. As engineer on the database infrastructure team, we provide a database as a service, DBAs, called DocDB as a function layer for our API. These guys use DocDB, which is a type of NoSQL database, but they built his own data layer on top of MongoDB community repository. So let's continue reading. Stripe.db is an extension of MongoDB community, a popular open source database, and consists of a set of services that we built in-house. It serves over 5 million queries per second, 5 million queries per second from a Stripe products application. Our deployment is also highly customized to provide low latency and diverse access, with 10,000 distinct queries shapes over petabytes of important financial data that live in 5,000 plus collection distributed over 2,000 plus database chart, this is insane numbers, guys. That's what I totally believe. If you want to get good as software engineer, you have to spend some time in this type of blocks, because you will understand how this type of company handle this type of loads that maybe are only accessible by them. We choose to build DocDB on top of MongoDB community because of the flexibility of its document model and its ability to handle massive volume of real-time data at scale. MongoDB Atlas didn't exist in 2011, so we built a self-managed cluster of MongoDB instances running in the cloud. At the heart of DocDB is the data movement platform, built originally as a horizontal scaling solution to overcome vertical scaling limits of MongoDB. Compute and storage. We customize to serve multiple purposes, merging underutilized database chart for improved utilization and efficiency, upgrading the major version of the database engine, our fleet for reliability, and transitioning databases from a multi-tenant arrangement to single tenant for large users. The data movement platform enables our transition from running a small number of database charts, each with tens of terabytes of data, which is a lot of data actually, to thousands of database charts, each with a fraction of the original data. It also provides client transparent migrations with zero downtime. Nice. Which makes it possible to build a highly elastic DBAS offering. DocDB can split databases chart during traffic searches and consolidate thousands of databases through being packaged when traffic is low. Okay, what we have onto here. So they build a DB like a SaaS solution, what I understand, or maybe a DBA's SaaS solution on top of MongoDB. And they built it with their own purposes to make data movement more fast when, specifically when traffic was low, which makes a lot of sense because you are just moving data when the least amount of user can be impacted for these writes and reads for your own charts, right? Let's continue reading. In this blog post, we share an overview of Stripe database infrastructure and discuss the design and application of the data movement platform. Okay, let's go to it. How we build our database infrastructure. When Stripe launched in 2011, we chose MongoDB as our line database because it offered better developer productivity than a standard relational database. This is totally true. You basically have higher throughput on a NoSQL MongoDB database, and you have more flexibility on your schemas, and you can even get higher throughput if you avoid certain type of transformation on your schema along the way, and you just insert the JSON, and after that you handle the transformation in a different way on your charts, or maybe by a different orchestrator. On top of MongoDB, we want to operate a robust database infrastructure that prioritizes the reliability of our API. But we could not find an off-the-shelf DBAs that met our requirements. Okay, meeting the highest standard of availability, durability, and performance. Exposing a minimal set of databases function to avert self-inflicted issue due to suboptimal queries from client applications. Supporting horizontal scalability with sharding. Okay, horizontal scalability with sharding. So they want different servers of the MongoDB that can able to create different charts. Okay, offering first-class support for multi-tenancy with enforced quotes, providing strong security through enforcement of authorization policies. The solution was to build DocDB with MongoDB as the underlying storage engine, a truly lasting and scalable DBAs with online data migration at its core. Product, application, and Stripe access data in their database through a fleet of databases proxy server, which we develop in-house in Go to enforce concerns of reliability, scalability, admission control, and access control, which is very cool though. They use Go instead of Rust. I told you, Rust is not good as you say it's good. I'm just kidding. I don't know what Rust is. I just haven't read a couple of blogs about Rust, but I think it's very hard to write. And let's stop here 1 second because this is one comment that I have in my in one of my videos here. Rust, it serves its own purpose, okay, but in my opinion, Go is going to be over Rust, and maybe in a couple of years. And if you don't believe me, you can go to. I think I have it here, so I can stop here to show you this really quick. You see, I was looking at the TOB index of the last month this morning, and you can see here Go is going higher at 1.16 change of rating of changes increase. So I don't see Rust in E here, okay, guys? So you guys that love Rust, you might have the reason for it. And maybe it's a good programming language to take a look and spend some time on it. From my just few hours that I spent on it, I believe that the performance capacity that you can achieve with this specific language it's how I explain this better. So Go is easier to understand, and you have a higher programming language that you can create reliable software with. It's easy to write, it's easy to implement, and it's very fast. Okay, so in most cases, if you have two languages that are fast, even one is faster but it's harder to write, and you don't have a base pool of engineers that can write it good, so you go to the easy with the easy one, because at the end, programming language, in my opinion, is just a tool. Okay, you choose a complex tool when you really need to use it. And for most software engineers, they are, unless you are, I don't know, unless you are in a AAA company that does a specific type of that build a specific type of services that need a specific feature that only ROS provide. So I think you shouldn't spend too much time on ROS, at least today. I think if you're going to, if I think we're going off a topic, but I think this is very important because I forget how to talk about this in the other video. Okay, but instead of going to ROS, just study a little bit of Go and try to get high performance backend services. Try to learn to implement those backend services with high performances with Go, and I think this is better use of your time right now. Okay, so let's go back to the deal here. So they use Go to enforce consent, reliability, scalability, and mission control, and access control as a mechanism to horizontally scale. We made the key architecture decision to employ sharding. If you want to learn more about database sharding, this is a helpful primer. So we're not going to talk about sharding today. Thousands of database shards, each housing a small chunk of the cumulative data, now underlies all Stripe products. When an application sends a query to a database proxy server, it parses the query, routes it to the one or more charts, combines the result from the charts, and return them back to the application. But how the database proxy server know which among thousands of charts to route the query to? They rely on a true metadata services that maps chunks to database charts, making it easy to look up the relevant chart for a query or for the given query. Basically, they have an orchestrator of the query that understands how and what specific server chart the query needs to be sent. In line with typical database infrastructure style, changes events resulting from writes to the database are transported to the stream software system and eventually achieve an object store via the data capture change data capture pipeline. Okay, this is the diagram. This is the Stripe API. We have the database proxy servers here. They somehow store the metadata, which they call change data capture, and after that they know how to synchronize this specific, or how to send these specific queries, or maybe synchronize this chart depending on that specific. That's what I understand. High level review of Stripe database infrastructure. At the product application level, teams as Stripe use the in-house document database control plane to provision a logical container for this data, referred to as a logical database, housing one or more docsdb collection and each comprising document that have a related purpose. Data in this docsdb collection is distributed across several databases, referred to as physical databases, each of which is home to a small chunk of the collection. Physical databases on DocDB live on charts deployed as a replica set that comprises a primary node and several secondary nodes with replication and automatic failover. Okay, so they have here somehow the logical DB, which have the shared collection between the chart's name and the database name. How we design the data movement platform. In order to build a database as a service, offering that is horizontally scalable and highly elastic. Elasticity is very important for this type of SaaS application. One that can scale in and out with the needs of the product application. We need the ability to migrate data across databases charts in a client transparent manner with zero downtime. This is complex distributed system problems. One that is further compounded by the unique requirement of important financial data. Data consistency and completeness. We need to ensure that the data being migrated remain consistent and complete across both the resources and the target charts. Availability. Prolonged downtime during data migration is unacceptable, as millions of business customers try to accept payment from their customers 24 hours a day. Our goal is to keep the key phase of the migration process shorter than the duration of the planned database primary failover, typically lasting a few seconds, and in line with the retrieve budget of our product application. Okay, they need consistency, data consistency, and completeness. They need availability over. Let's continue reading. Part granularity and adaptability. At Stripe scale, we need to support the migration of an arbitrary number of chunks of data from any number of sources to target charts, with no restriction of the number of in-flight database show migration in the fleet, and no restriction of the number of migration any given chart can participate in at any point in time. We also need to accommodate the migration of chunks of various sizes of high throughput, as several of our database charts contain terabytes of data. No performance impact to source chart. When we migrate database shown across chart, our goal is to preserve the performance and throughput of the source chart to preclude any adverse impact on performance and available throughput for users query. To address this requirement, we built the data movement platform to manage online data migration across database chart by invoking purpose-built services. Okay, I'm trying to understand this specific graph. Basically, they have a proxy server, they have the metadata for the queries and the data that needs to be migrated somehow between charts. Okay. The coordinating component in the data movement platform is responsible for orchestrating the various steps involved in online data migration. It invokes the relevant services to accomplish each of the constituent and step outlined below. Yeah, they have like emitter services here, which maybe is an orchestrator. They just call it the DB control plane, which manage this data. But how this is a specific build? Let's see if we find some of that information. Step 1, show migration registration. First, we register the intent to migrate database chunks from the source chart to arbitrary target charts in the show metadata services. Subsequently, we build indexes on the target chart for the chunk being migrated. Okay, so step 2, book data import. Next, we use a snapshot of the chunk of the source chart at a specific time denoted as time t to load the data onto one or more database chart. The service responsible for performing book data import accept various data filters and only import the chunks of data that satisfy the filtering criteria. While this step appears simple at first, we encode it through limitation when book loading data onto DocDB charts. Despite attempt to address this by batching writes and adjusting DocDB engine's parameter for optimal bulk data ingestion, we had little success. However, we achieved a significant breakthrough when we explored methods to optimize our insertion order, taking advantage of the fact that DocDB arranges its data using a B-tree data structure. By sorting the data based on the most common index attribute in the collection and inserting it in the sorted order, we significantly enhance the proximity of writes, boosting write through 10%. This is very important. And this is why I believe understanding data structure is important, even though you are not going to interview for any fan, because you understanding the data structure. Data structure is underlying piece of control for any algorithm and any system, any process. Is a group at the end is a group of algorithms that uses this different type of data structure. So they were able, by just understanding how the indices were built with the type of indices, the data structure type, they were able to increase the write throughput by 10 times, which is insane. Why? I have to put this note here. I have to understand. Yeah, I was taking this note because I want to understand. It's been a long time since I used a B3 data structure. So I suppose that when you are going to insert in a B3 data structure and the other collection is sorted, you will get lower O operations, because it's faster to go for the nodes. It's faster to go each node by node. You don't need to go in one node and after that find the other. Go, yeah, that should be the answer. But I want to find the clear technical answer, so I took the note here for me to understand this accurately. But basically, it's just because you have a B3 data structure, which is a binary tree, where it's easy to insert, because at the end you're just going one level down or one level down, and you don't need to go to the root and go back to the nodes, root to the back to the node, if the collection you are inserting is not ordered. So um, that's what I believe. Okay. Um, Async replications. Once we have imported data onto the target chart, we begin replicating writes starting at times t from the source of the target chart. For the database shown being migrated, or our async replication system read the mutation resulting from writes on the source chart from the CDC system and issue writes to the target chart. The operation logs and special collection, to keep the record of operation that mutate data. We transport the upload events from every DuckDB chart to Kafka, okay, which is just a service broker with high throughput to an event streaming platform, okay, and then achieve it to a cloud object storage service such as Amazon S3. Okay, they just basically create a file here or blob file here, and they keep persist the data inside there. If you want to learn more about oblogs, this is the help. Okay, I haven't read anything about oblogs. We build a service to replicate mutation from one or more source DuckDB charts, more target.db charts using the oblog events in Kafka and Amazon S3. We rely on the oblog event from our CD system to ensure that we didn't slow user queries by consuming read throughput that will otherwise be available to users' query on the source chart, and to avoid being constrained by the size of the oblog on the source chart. We designed the services to be resilient to target chart unavailability and to support starting, pausing, and resuming synchronization from a checkpoint at any point in time. The replication service also exposes the functionality to fetch the replication lag. Mutation of the chunk under migration gets replicated bidirectionally from the source chart to the target chart and vice versa. And the replication service tags the right is issued to avert cyclically asynchronous replication. We made this design choice to provide the flexibility to revert traffic to the source chart of any issue. I actually don't understand anything of this paragraph. I'm going to copy here because I want to understand it later. Okay, but basically they have a metadata, they call CDC metadata type of, and they push it through a metadata type of logs events. They use Kafka to stream this data into Amazon S3, and from there they're able to use these specific logs to rebuild the historical. This is what I understood: the historical of this type of specific logs, transactions, if we can call it that way, into your system back. Okay, and step 4. Correct the checks. After the replication sync between the source and target chart, we conduct a comprehensive check for data completeness and correctness by comparing point-in-time snapshots. A deliberate design choice we made in order to avoid impact charts throughput. I think this decision was very risky to do, because if you are if you have 2,000 plus charts and you are comparing snapshot between all of them, or maybe I'm not able to understand how the all logs template or metadata contains but I'm able. Yeah, maybe it's because I don't know. I don't know why they did this, to be honest with you, but I believe um, they did it right, right. But I'm not sure if this was the best thing to do. But I believe at the database level, it's better to validate the correctness, which I believe this is why they did this. If you're going to do it at the application level, you need a complex orchestrator to validate all the hatches between the data set that you are going to compare. And if they have such amount of charts, amount of chart over 2,000 plus chart databases, so they maybe that's why they choose this path. You have a lot of way to reconcile the data between different services, different databases. And I believe from this, what they are explaining, this is why they use this one. Okay, this is strategy. And step 5, traffic switch. Once the data in chunk is imported from, as you can see here, this is very complex stuff, guys. Okay, so don't smile if you feel that I'm not able to understand this accordingly. Okay, or maybe you smile, whatever. But I don't care, to be honest. I'm just trying to do the research at the same time and learn together. And you share your comments here. You can criticize. You can do whatever you want. I just will continue helping you understand this better at the same time. Just learn a little bit. Okay. This is very complex things. So they have managing this amount of databases and data set and chart is very complex. So spending some time on this specific blog post is important. Maybe in your lifetime you will not be able to handle such amount uh, of data. Okay, but it's important to understand it. On my opinion, it's very important you spend some time, because most of the time on the API based system and applications, the bottlenecks is often on the database strategy you use, on the data layer you use. So understanding this is very important as a backend software engineer. As a general software engineer, but if you are a backend, it's very important to you for you to understand the different strategies that these companies uses to configure the data layer. Okay, let's see if we can understand this one. We are almost finishing here, so we're very close to the finish line. So step 5, which is the latest, almost the latest step. Once the data in a chunk is imported from the source of the target chart, any mutation are actively replicated. A traffic switch is orchestrated by the coordinator in order to reroute reads and writes to the chunk of data being migrated. We need to first stop the traffic on the source chart for a brief period of time, update the resource in chunks, metadata service, and have the proxy server redirect reads and write to the target chart. The traffic switch protocol is based on the idea of versioning gating. In steady state, each proxy server annotates requests to DuckDB charts with a version token number. We add a custom patch to MongoDB that allows a chart to enforce that the version token number it receives on request from a proxy server is newer than the version token number it knows, and only serve requests that satisfy this criterion. To update the route for a chunk, we use the coordinator to execute the following step. Yeah, basically they have the charts going in and down. They put the charts down, they do the migration, they put the charts on again. This is the diagram. So we have a client app that makes the query, the proxy server create the version equal 1, send the result to the client app. But we already have the data here, right? After they send the result, we have a coordinator which increase the version, say an okay response, show me the data service. If replication is in sync, if the replication is in sync, they active the replication service. Replication service responds with okay, I'm able to replicate. Coordinator is able to check if the replication is in sync. If it's still in sync, they update the version, say okay, fetch new routes. So that's how all the workflow of the traffic switching process works. They basically have a sources and a target, right? And maybe this is just the same chart. I'm not sure. Maybe this is just one database, and this is the couple of charts. But this is how they integrate all the data, and they persist all the data, and consistently have um, the data across all its own charts. Okay. So when they complete all these transactions, the processor will fetch the update routes for the chunk and the most up-to-date version token number from the chunk metadata services. What I don't understand here, which I think is very important, is how they split these chunks by day, by hour, by minutes, by seconds, or maybe it's just a query selecting a specific limit. The entire traffic switching protocol takes less than 2 seconds to execute, and all failure read and write directed to the source chart succeeds on retry. Oh, nice. So the first one, if the this is very smart. If one request fails, this traffic switching is so fast that the second. That's what I believe is so important to apply retries on your request. Yeah, at least 3. Okay, at least 3 retries. Step 6, which is the latest one, show migration deregistration. Finally, we conclude the migration process by marking the migration as a complete in the show metadata service and subsequently dropping the shown data from the source chart. So then they continue. So then the charts keep increasing, which is the target databases, right? And stores maintain a specific amount of data, which will impact the reading and writing from the client application directly. Okay, so you will have a lot of data here, but you will not impact the data, the client app with the sources, which is, I think, this is very good strategy though. Okay, this is the conclusion, and we're going to conclude with this. I hope uh, you like this specific blog. I'm going to put the blog post at the end and the YouTube video descriptions. I think this is a very cool strategy. I wasn't able to understand completely, to be honest with you. I'm going to review this one later, maybe another video, maybe not. But I need to understand a few ideas here that I wasn't able to understand, and maybe serve as a jumping challenge for you to help me understand this too, right? But in general, the ability to migrate chunk of data across DuckDB charts in online manner help us horizontally scale our database infrastructure to keep pace with the growth of Stripes. Engineers on the database infrastructure team are able to split DuckDB chart for size and throughput. Okay, this is the answer the question that I just made. It just got answered here. They use a specific limit of size. That's how they chart and split the chunks of the databases. And throughput with a click of the button, freeing up database storage and throughput headroom for product teams. In 2023, we used a data movement platform to improve the utilization of our database infrastructure. Concretely, we impact thousands of underutilized databases by migrating 1.5 petabytes of data transparent to product application and reduce the total number of underlying.db charts by approximately 3/4. We also use the data movement platform to upgrade our database infrastructure fleet by forking lifting data to a later version of MongoDB in one step, without going through intermediate, major, and minor versioning with an in-place upgrade strategy. The database infrastructure team at Stripe is focused on building a robust and reliable foundation that scales with the growth of the internet economy. Okay, here goes, guys. I think this strategy, it was one of the main important reasons they were able to handle such amount of requests in 2022, which I believe was a great achievement on their side. They also have other ideas that I'm not going to I'm not going to explain here right now in this video because I don't want to make videos so long. You get bored so fast. But the whole idea is they have idempotence, they have a specific versioning. They spend a lot of time designing a unified API, which makes the data set of the request unified for any type of transaction, any type of payment you want to do. They have done a lot of things in order to make this API much better. Of course, it's many years, over 13 years of building and shipping features, which I believe how long, how much Stripe. Um, what is the market cap of this? Are they public or? Okay, there you have 65 billion valuation by Goldman Sachs. When this is on February 2022. Maybe they are worth more right now. Um, let's see. Is a stripe. I is a stripe. Is a stripe public? Why am I not able to find it? I bet that they were open to uh, public trading, but they not. So you have a 70 billion company using one MPI. This is what the point that I was trying to make. But it's a great product. It's a great product, and the million of users of any type using them. So that's what I believe you should spend some time learning how they build this API, because it's going to give you a lot of good insight that you haven't seen on all the documentation that I just shared here below. See you in the next video. I hope you like it. I'm Carlos Corrales. Bye.